So the self-structuring protocol is very simple. It basically just means perturb the system and let it relax, and do that repeatedly. So at some interval, we're going to reset all of the state configurations of the system and let them relax again. Now, the extra conditions are that we need to get some time constants right. So it needs to be the case that the system spends most of its time at local optima, so you can't perturb it too frequently, and it needs to be the case that the changes in the strength of the springs happen gradually, so they don't just relax immediately on the first thing they see. Yeah? So here's some examples of, these are the endpoints. I showed you 10 example runs, and they had different local, they found different energies, so that would be the first 10 points here, and that's just some more examples. 400 examples of the local minima found by system A. And this is what happens to the distribution of local minima found by the system as you condition it, just by perturbing it and allowing it to relax whilst the springs are changing their tension. And you find that over time, it relaxes the springs in such a way that the configuration that B finds, there's only one configuration that B finds, and it's the minimum energy configuration of the system A. So there's the distribution of histogram of the energies of A, and the histogram of the energies of B after conditioning. So, some caution with naive interpretation, what this isn't, right? I could be saying something like, well, I'm relaxing the tensions in the system by changing the energy of the system, by changing the springs in the system, and then I'm relaxing them, so now the energy is lower, so the system is lower in energy, and there's no magic at all. But that's not what I'm saying. That's not what I'm saying, because I'm reporting the energy of the configurations using the original stored values, which I did at the beginning. Right, that's that configuration of the system. If I applied that configuration to A with the original springs would be lower energy, right? So B is better adapted, not because it's changed the energy of any particular configuration, but because it's finding different configurations. So how does it work? Basically, it works because some constraints are consistently unsatisfiable. So weakening springs that are consistently in tension has the sense of creating new dynamics that pay less attention to the constraints which are consistently unsatisfiable, which means that it pays relatively more attention to the constraints which are satisfiable, and that causes it to avoid the local optima which are created by conflicting constraints. So that's a sort of simple way to understand it. It's not quite as simple as that, though. I want that explanation to give you slightly more thing. Oh yeah, I get that, I know how that works, so now I'm going to upset that a little bit. We're trying to minimize the number of constraints that are violated or remain unsatisfied. So how can ignoring unsatisfied constraints improve things? Which constraints remain unsatisfied depend on what configuration you're in. So the impetus in some configurations is to weaken some springs, and the impetus in other configurations is to weaken others. If they were, on average, they were weakening all of them, it wouldn't make any difference. So we can understand how this works using theory from neural networks. And that's because plastic springs basically do heavy learning. So heavy learning in neural networks, okay, says that we should change the strength of the spring in proportion to the product of the states. So if the two states are the same, we should increase the strength of the synaptic connection, and if they're different, we should decrease it. So if they are different from one another, in this system it's the other way around, because the springs are keeping things apart. But it basically means the springs which are in tension when you relax them, they do half of the work of Hebb's rule. So if I was to do the full work of Hebb's rule, then it should be the springs which are relaxed or made stronger so that they push things apart further. But I don't need to do that half. I can just do the easy half, which is to weaken the springs which are in tension. And because relatively it makes the other springs more tense, that will work fine. So since the system approximates Hebbian learning, we can understand that as it's forming a memory. What's it forming a memory of? It's forming a memory of its own attractors. I said that I would perturb it in such a way that it spent most of its time at local minima. So it's forming a memory of its own attractors, which causes it to go to the local minima which is visited in the past with higher probability, increasing the basic attraction of those local minima. Well, that doesn't sound like it's going to do any optimization. That's just going to make going to local optima more likely. How does forming a memory of local optima make you go to the global optima? Well, that's to do with the relationship between local optima and global optima in a system of this sort. And because we understand exactly what sort of generalization Hebbian learning in a neural network can do, we can understand exactly the conditions under which this kind of adaptive process is capable of finding global optima by generalizing over local optima. So no algorithm can solve all problems. It has to be the problem that's built out of a superposition of pairwise constraints, which is the kind of problem I set out to solve in the first place. Is this a hard problem? Well, it's a problem that a hill climber doesn't solve as well as this does. Is it a relevant problem? Well, it's a problem that many natural systems involve the superposition of conflicting pairwise constraints, like species competing for a resource. So we've demonstrated the same sort of dynamics in a number of different systems now. A talk I'm giving tomorrow is about the same dynamics in gene regulation networks. Adam Davies on the last day is talking in the plenary talking about games on networks, optimization in complex adaptive systems like a grid computing scenario, and the evolution of cooperation where individuals can change their own population structure and hence the level of cooperation. So the real motivations for the talk are that those systems are systems which do this kind of adaptation, but somewhere in those models there is some natural selection. So I wanted to do the same system, the same kind of model, but remove all of the natural selection from it so we can see that the process which is creating the adaptation isn't natural selection. So the claims, just the last slide. I've shown the conditions where a simple dynamical system can be conditioned to perform optimization better than local search. It's fundamentally motivated, the way that it works is fundamentally connected to robustness or reducing the likelihood of things changing over time. And hence it is deeply related to notions of self-regulation or pangeohomeostasis and homeostat that we're familiar with already. But it's formalized in an optimization framework so that we can quantify exactly how good it is and what kind of optimization it can do, and relate it to the formal theoretical framework of associative learning. So dynamical systems with plastic connections do that sort of adaptation spontaneously, and this is part of a bigger argument where I want to say that systems like ecosystems and social networks and multi-agent systems also do that kind of adaptation, but not by natural selection, but by this kind of conditioned relaxation. So I'll stop there.